Okay, we're gonna continue on here, finish up the gas chapter, I believe. So last time we were talking about gases. We talked about a couple things. We talked about figuring out the molar mass of a gas and also the density of a gas. And again, molar mass is grams per mole and density is grams per liter. So we saw a couple of formulas where you could directly just kind of put it in to calculate each of those things. And as we talked about, if you can't remember perhaps those formulas or don't really want to remember those formulas, you really can still use the ideal gas law really to sort of derive both of those formulas as they sort of come from it. So using PV equals nRT will allow you really to sort of solve for both of those things. The molar mass is pretty straightforward. Usually in those type of problems, somewhere in the problem, they will give you the grams of the gas. So what we would use the ideal gas law to help us figure out is really the moles. So N is equal to PV over RT, and that would get us to sort of the moles part that you would need. So once again, if you don't want to remember that other formula, just think about sort of the units and using the ideal gas law to get you to what you need in terms of the molar mass. Now, in terms of density, is kind of the same situation. We had a formula where you could straightly plug in there to figure out the density. But again, it really is derived from the ideal gas law. And in this situation, we actually would be solving for N over V. And N over V would be P over RT. N over V is moles per liter, and that's basically the molarity of the gas. And once you sort of solve for moles over liters, at that point, you could actually use the molar mass of that gas, and the moles will cancel, and that will basically get you to the density. So those formulas that we saw earlier, again, are pretty much derived from the ideal gas law, and you could kind of get them from there without maybe the hassle of remembering those couple of gas laws. Towards the end, we talked about stoichiometry involving gases, and it's really the same sort of steps that we want to follow when we're doing normal stoichiometry problems that involve gases. Basically, we got to always make sure we got our balanced equation. We want to convert to moles. We want to do the mole to mole relationship. And then we want to take those moles to some other unit. Again, in most cases, somewhere along the way, either at step number 2, you're going to use the ideal gas law, and probably you would use it to solve for moles, which would be PV over RT if you did use it at that step. If not, most commonly at the end of the problem, using PV equals nRT and solving for something like the volume of the gas that you would collect, which is also a very common sort of outlet of it. So somewhere along the way, usually in these type of problems, you got to insert that ideal gas law. In some cases, maybe both places, you might do it. The other thing that you also have to watch out for, as we talked about, is again, you could still have some type of limiting reagent type of problem that may occur, even with gases or solutions or any of those type of things. So they can have multiple types of problems. You just got to make sure you don't have to figure out the limiting reagent. If you do, you basically just figure out the limiting reagent somewhere around that step, if it happened to be, and then you could kind of continue on. Once again, if it is a limiting reagent problem, some way, somehow, based on the information given to you, you would be able to get to the moles of each reactant. So again, that's basically how you know you have to do that step. Any questions on any of that stuff there? Okay. So next thing we're going to talk about is partial pressures. Dalton's law of partial pressures, which sometimes makes people think sounds very hard with the title like that. But it's a pretty simple sort of concept. And the idea here is much like the pictures show, if we had a container that had just one gas molecule in it or one type of gas molecule, when we would look at the total pressure associated with that, it would pretty much all be based off of that one gas molecule that's basically flying around and causing collisions. Oftentimes, though, gases do come as mixtures. So, if we had gas molecule A, gas molecule B, maybe gas molecule C flying around in that particular container. In this case, the total pressure would be a result of all three gases basically moving around, pressure of A plus the pressure of B plus the pressure of C in this case. And since they all sort of contribute to the overall pressure, which is usually your barometer reading and your atmospheric pressure, these are what are known as partial pressures. Now, partial pressures of A plus partial pressure of B in this case, plus partial pressure of C is going to give us our total pressure. So there's a couple of different ways that you can actually get the partial pressures of a gas. Probably the most convenient way or very common way is to still use our good equation here, the ideal gas law, and basically solve for P for each gas individually. And you could do it for A, B, and C. The nice thing about it is that they are in the same container, which means for all the gases in that mixture, they will all have the same volume. They're also probably sitting in the same shelf or wherever they may be in the same room, which means they also have the same temperature, which means when you look at the ideal gas law for your different gases that you may be sort of calculating, with R being a constant, pretty much the only sort of difference in the calculation that you're going to do for the different gases is the number of moles that you have for each of those gases. So you basically would just plug everybody into the ideal gas law individually, get the pressures of each of those guys, which would be their partial pressures. And then again, to get the total pressure, you would just add them together. Any questions on that there? Now, why can we do this? We could really do this type of calculation because of the situation of an ideal gas. So we've been talking about the ideal gas law and gases being ideal. And one of the major sort of considerations that make something an ideal gas is the idea that we assume in ideal conditions that gas molecules pretty much don't interact with each other. That means there's no attractive forces between different gas molecules in an ideal situation. There's no repulsive type forces between the gas molecules in an ideal situation. And that means that essentially when we have a mixture of gas like we do here, we could almost assume that each of those gas molecules are in that container by themselves, as there's going to be no interaction with the other gases that are present. And that allows us to do basically the ideal gas law for each of those. A little later on here, we're going to talk about non-ideal conditions where you do have to take that into account. But here in these sort of ideal conditions, we could just use the ideal gas law and take that assumption that even though there's multiple different gases flying around, there's not going to be any type of interaction is going to happen between them. So in general here, you could really, like I said, just go into that ideal gas law and plug and chug and solve for each of those gases and get the partial pressures. Now, there could be a situation where maybe you don't really have enough information to go into the ideal gas law. Maybe you don't have some temperature type situation or volume situation, but you do have a couple of important pieces of information. One piece of information that would be important is you have the ability to figure out the moles of each gas. So either you're given the moles of each gas, you're given the grams of each gas, whatever it may be, and pretty much one pressure sort of value, either the total pressure, somebody's partial pressure, or something like that. So if you have sort of that limited information, there's another formula that you could use that will help you sort of calculate partial pressures and also the total pressure of a gas mixture. And that is this one down here. This is the partial pressure of a gas. This is the mole fraction of that component. If you remember, we talked about mole fraction in the last chapter. The mole fraction is kind of like a percentage without the multiplying by 100 part. You take the moles of what you're interested in, divided by the total moles, and don't times it by 100. So you get kind of the decimal form of it, which is really still a percentage. But we take the mole fraction times the total pressure here. So in a situation where, again, you may not have enough information to go completely into the ideal gas law, but you do have that moles information, or able to get to the mole information. And again, with that, you would need some type of pressure value. Once again, either total pressure or at least one of the partial pressures. You could use this formula as well, which is a handy dandy little formula there as well. Any questions on that? All right. So let's take a look at one here. See what you come up with. We have 5 grams of helium. We also got 5 grams of neon in a 2.5 liter container at 27 degrees. What are the partial pressures of each of these gases, and what is the total pressure? So helium is 4.003. Neon is 2018, I believe. All right, let's take a few minutes, see what you come up with. Okay, so let's take a look. So in this case, we obviously have a mixture of 2 gases. We have some neon flying around, got some helium flying around. And we could assume that, they're sort of in there by themselves. So we can use the ideal gas law for each of them and really solve for pressure. We do have the volume given to us at 2.5 liters. We do have the temperature at 27 degrees Celsius. Obviously, since we are using the ideal gas law here, we do need to convert that into Kelvin. So that's going to give us 300 Kelvin when we add 273 to it. We want to calculate the pressure of each of these guys. Once again, we always have R, which is our gas constant. So we are missing the moles. We have the temperature, we have the volume, we always have R. So we are missing really the moles here to be able to solve for the pressure for each of these. So that's the first thing we want to do, really, is use the molar mass and convert each of these guys into moles. So we got 5 grams of helium. Using the molar mass from the periodic table, 4.003 grams per mole. We'll do the same thing for our other gas, which is our neon, and we'll do 2018, it looks like, grams per mole. And that's going to get us here. Looks like 1.25 moles there for helium. And for our neon, 0.248 moles. So now we have really the missing piece of information that we need for each of these. We're going to go into the ideal gas law twice here, and we're going to solve for P. So we'll do it for helium first. That's going to give us nRT divided by V when we bring this guy basically to the other side and divide. Putting in our numbers here for helium, 1.25 moles. Our gas constant, our temperature 300, all divided by our volume of 2.5 liters. Moles will cancel, Kelvin will cancel, liters will cancel. Going to leave us atmospheres, which is good since we're looking for a pressure in this case. And it's going to give us 1.25 times 0.08206 times 300 divided by 2.5. Looks like a 12.3 atmospheres. This would be the partial pressure of helium in this case. Any question on that calculation there? Yeah. They are not. So they're noble gases. So those are all monatomic. So only like those like nitrogen, oxygen, hydrogen, chlorine, and fluorine, they're going to be diatomic. Yeah, but that group 8 are monatomic. Other questions? All right, so we're also going to calculate the partial pressure here of neon, which is pretty much the same calculation. Really, the only thing that's going to differ is the number of moles, as they're basically both in the same container. So we'll use the moles for our neon here, 0.248. Everything else, again, going to be the same. Once again, the same units are going to cancel. Going to again leave us with atmospheres here. And for our neon here, 0.248 times 0.08206 times 300 divided by 2.5 looks like a 2.44 in terms of its atmosphere. And this would be considered the partial pressure of neon in this case. At this point, to get the total pressure, all I really have to do with both of those numbers is just add them together. So the total pressure here is going to be our partial pressure of helium plus our partial pressure of neon, which is going to give us 12.3 plus 2.44 atmospheres. We'll try it without the calculator. 14.7, I hope. Atmospheres will be our total pressure in this case. Question on that there. Yeah, so if you look kind of in the problem itself, pretty much everybody has three significant figures. Now the temperature, when you do convert it, becomes 300 on the nose. So you probably would actually keep 3 sig figs, as you would want to go to a whole number in terms of the adding part. Because when we do temperature conversions, we want the converted value to look like the original one. So if we took it to 300 and only kept 1 sig fig in that case, it would obviously cut it too far. So you probably would keep all the zeros there. And that would basically give you 3 sig figs across, except for the gas constant, which obviously is 4 in this case. So that's why we ended up with something like 3 for the individual partial pressures. And then when we added, we went to decimal places. So 1 decimal place is where we cut it off at the end there. Yeah. Other questions? The major contributor to this pressure is which gas? It is helium, right? Reason why it is because it is much lighter. Yeah, it's 4 versus 20. So it's actually a lighter gas, which we'll talk about shortly here. It actually is moving at a much higher velocity, which means it's going to be banging around, causing a lot more collisions. And that's why it's made the major contributor here to the pressure, as opposed to the heavier, slower moving neon in this mixture. Any questions on this? So this is one type of partial pressure type problem, which is essentially really just an ideal gas law done separately for each gas in the mixture. And really the only difference in the calculations should be the moles of each of those gases. Let's take a look at another one here. We have a sample of natural gas is 8.2 moles of methane, 4.421 moles of ethane, and 0.116 moles of propane. The total pressure is 1.37. Okay, so let's take a look at this one. In this case, we definitely have moles of everybody in this mixture. And we do have a total pressure, but we really have no other information about, volumes or temperatures or anything like that. So this is a situation where we really can't use the ideal gas law that easily, but we can use that other formula that we saw, which involves the mole fraction, which we do have the moles of everybody here. Obviously, if we're given grams as well, we could use the molar mass to convert to moles if needed to. When we do have the total pressure, which is the other sort of key component to be able to use this, is you don't necessarily have to have the total pressure, but you need at least one pressure sort of value given to you. So in this case, we're interested in the partial pressure of propane. So we do want to calculate the total moles here. And we'll get that by taking our 8.24 plus our 0.421 and our 0.116 in this case. That looks like we're going to get 8.777 moles. To find the mole fraction here of our propane, we're going to take the moles of propane, which is 0.116, and we're going to divide it by the total moles. Once again, here we're not going to multiply it by 100, so we're going to get kind of the decimal form there. And we got something like 0.0132, basically 1.3% of it is our propane. Now that we have the mole fraction and we have the total pressure, we can find the partial pressure here of our propane by taking our mole fraction for the propane. We're going to times it by the 1.37 atmospheres, basically taking 1.3%. And that's going to give us that our partial pressure here of our propane is going to be 0.0181 atmospheres. Question on that there. We could also do this for any of the other gases. So if we wanted the mole fraction, for example, of methane, it would be the moles of methane, 8.24, divided by our total moles. And for methane here, going to give us a mole fraction of 0.939, basically 93% or 94%. We then could put that into our equation for methane if we were interested in it. And that would give us 0.939 times our 1.37 atmospheres, going to get us there approximately 1.29 atmospheres. So that would be our partial pressure there of methane. We could also do the same thing for ethane, or at this point, since we already know the total pressure is 1.37 and we got two of the three, we could just add those two together and subtract from the total pressure, and that would get us our partial pressure of the third gas as well. Here we see that it is methane in this case. It actually is the major contributor here, again, to the total pressure. Couple of reasons. Obviously, there's more moles of it flying around, so there's going to be more collisions. And out of those three, methane is still the lightest of all three of those. So it also will be flying around a lot faster, contributing more to the pressure. Any questions on this version of a partial pressure situation? So again, this is a good one to use when you're sort of limited on information, but as long as you got those two pieces of information, able to get the moles and at least one type of pressure, you could use this to calculate the other partial pressures. Any questions on that one there? All right, now a third type of partial pressure is one such as this. So very often when we do collect gases, a lot of times what we do is we kind of, to figure out the volume of the gas that we collect, we oftentimes will do really like a displacement of water. So we'll have sort of a receiving beaker or jar, such as what we see here. And as the gas kind of goes into that receiving beaker or jar or tube, the water goes out and sort of displaces the water. So in this case, if we were to heat up some potassium chlorate, it would go through a decomposition reaction, produce a little potassium chloride and some oxygen gas. So in this case, you would be producing some oxygen gas. This oxygen gas is going to go through the tube as it's got nowhere else to go. Going to go up and start bubbling, as we can see here, into the water. Water will leave the jar, and in this empty space, you will end up with your oxygen gas in this example. But the consequence of sort of collecting your gas this way is I'm doing a little reaction, and that's probably going to have some heat or something involving water. Water and heat creates water vapor. So we'll also collect some water vapor along with the oxygen gas in that area. And this is the water vapor. The problem with that is we're not really interested in the water vapor. It's really just a side effect of how you're collecting your gas, like a contaminant almost. So in this partial pressure situation, what happens is we usually want to get rid of the water vapor's contribution or the water's contribution to the pressure. So in this situation, what we will have is that the total pressure will equal the pressure of the gas we're interested in, which in this example here is oxygen, plus the vapor pressure of water. And that's what that is referred to, the vapor pressure of water. That is usually a table value. You look that up in a table based on temperature usually, and it will give you the vapor pressure of water. So in this situation, what usually will happen is we will rearrange that equation and solve for the partial pressure of the gas we're interested in, and that would be our total pressure minus the vapor pressure of water. The total pressure here would really be your barometer reading if you were doing the experiment. Atmospheric pressure, if you were doing sort of a book problem. This is sometimes referred to as getting the pressure of the dry gas, since you're sort of subtracting off water's contribution to it. So that sometimes is use that wordage or verbiage there when we do it. So that is a very, very common sort of partial pressure problem that sort of develops. And it's really, again, just a byproduct of how you collect the gas. Usually sort of the key words that you see in problems that tell you that you probably got to go find a table of the vapor pressure of water is a usual mention something like your gas was collected over water, or it's saturated with water vapor, or something's mentioned about water and sort of the collection of the gas. And that usually means you need to do really this sort of correction calculation, which is not too bad since it's really just subtraction in most cases, and subtract off the vapor pressure of water's contribution. Any questions on that there? So here's an example of that table. And again, as you can see, basically look it up at temperature, gives you really that sort of correction value that you could use. So let's take a look at a problem like this. Why don't you give it a go? A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr, and the vapor pressure of water at 30 degrees is 31. Okay, so in this situation, the sort of key word there or phrase that wins here is that we are saturating it with water vapor. So again, this tells you it's sort of that situation that we were just talking about, that the total pressure is the pressure of the gas we're interested in plus the vapor pressure of water. And in this case, the gas we're interested in is oxygen. It's pretty much that same experiment we just looked at in that picture. If it was not given to you in the problem, which it might not be, you may again have to reference a table like we just saw on the previous slide there. And we would look it up at 30 degrees Celsius to find the vapor pressure of water. And we are given the total pressure here that I scribbled all over, but I think it says 753 there. So in this case, we have 753 torr, which is our total pressure, equals the partial pressure of oxygen plus the vapor pressure of water at 30 degrees, which is 31.824 torr. So the partial pressure of oxygen would be our 753 minus 31.824 torr. And that's going to get us there. 753 minus 31.824. About 721 torr. Again, though, we are interested in atmospheres, so 1 atmosphere is equal to 760 torr, or 760 millimeters of mercury. So doing our conversion, 721 torr, we're going to divide by 760 in this case, gives us our atmosphere. 721 divided by 760 gets us a 0.949 atmospheres. And that would represent really the partial pressure of just our oxygen gas in this case. And once again, if we did this experiment, that is really the pressure we're interested in. We don't really care about sort of the contribution that water is making, as again, it's sort of a contaminant as a result of how the gas was collected. Any questions on any part of that calculation there? You don't, because we're really not using it anywhere. The temperature is really here to let you know where on that table to go look up the vapor pressure of water. So in this particular case, that's really why I would say probably in a lot of book problems or something like that, they probably won't even give you this part. So they would just kind of give you that front part. And that's really what the 30 degrees is to tell you to go to like this table and go, okay, 30 degrees. That's the vapor pressure of water, basically. So That's sort of what the temperature is there for. We're not going to really use it in the calculation other than sort of a guide to go find the vapor pressure of water. Yes, guys. Other questions? So those are three sort of different partial pressure problems that you may come across. One most common, probably ideal gas lawing it up for everybody. Secondly, not enough information to go into the ideal gas law, but you do have moles and a pressure, so you could use the other one. And the most common sort of partial pressure situation that develops when you actually do a gas experiment is sort of the last one there, just as a result of how you collect the gas. You're going to have to correct for that vapor pressure of water. Any questions on partial pressures? All right, so let's talk a little bit about the kinetic molecular theory of gases. And a gas is composed of molecules that are separated from each other by greater distance in their own dimensions. The molecules are considered to be points and their volume considered to be negligible or zero. And this first one here, or this part of it pretty much, is one of the reasons that we sort of consider something an ideal gas. And part of being an ideal gas or under ideal circumstances is the idea that the volume of the gas itself is relatively small compared to the size of the container it's flying around in. So usually if you think about a lot of the problems that we come across, they oftentimes will talk about the container's volume that the gas is in rather than the volume of the gas itself. And that's because in ideal situations, let's do it like that, the gas volume is much, much smaller than the actual volume that is flying around in. So the container's volume is more important. We assume in an ideal situation it's flying around and filling this uniformly. So the whole container is sort of its volume rather than the addition of the volume itself. We'll talk about it in just a bit here, but under non-ideal situations, you can't do that. The volume of the gas itself is important relative to the volume of the container that it's in. A gas molecule is in constant motion and directions with one another. Collisions are perfectly elastic. That's sort of the idea that, you know, they just kind of bounce off each other, not going to really kind of stick or anything to each other. And that brings us to number 3, which is really kind of the other part of the deal there that makes something an ideal gas. And that is that gas molecules, again, exert neither attractive forces or repulsive type forces with one another. And in an ideal situation, that is what gives us the ability to do that partial pressure problem like we did, where we had 3 different gases or 2 different gases in the same container, and we could just think about them as being there alone, that they're not going to participate with one another, as we'll see in just a bit. If we did have, for example, 2 gas molecules, and in an ideal situation, this gas molecule is pretty much free to slam into the wall and cause some pressure situation happening. But the idea here is if this gas molecule, for example, was attracted, say, to the guy behind it, there's going to be some attractive force kind of pulling him backwards away from that wall. And that's going to have an effect on the rate of collision that he might have. So in a non-ideal situation or a real gas situation, those attractive forces will have a role in terms of affecting the pressure. But in an ideal situation, we just assume they're just going to whiz by and no worries about anybody else that may be near each other. So there's nothing that's going to impede its sort of progress as it's flying around, and it will have really no effect on the pressure. And that's those 2 main components there that really does make something sort of the ideal gas in an ideal situation. The last sort of part of this is the average kinetic energy of a molecule is proportional to its temperature. So if we increase the temperature, we do expect, obviously, our gas molecules to fly around faster. And if we lower it, it should fly around slower. We're not going to calculate any kinetic energy, but that's the calculation for it. So some of the things that we saw in terms of our relationships, as we went through the different gas laws, we saw with our Boyle's law again, the pressure increases as the volume decreases, as everybody sort of slammed into a much smaller area, which is going to increase the rate of collisions. And vice versa, as we increase the volume, we see a drop in the pressure because, again, everybody has a little bit more room to fly around in. It's going to take a little longer for collisions to occur, and the pressure is going to come down. In the Charles law situation, we have V1 over T1 equals VT over T2. And again, in that situation, to keep it constant pressure, the volume does adjust as the temperature increases because they're going to be moving faster, which means if the volume did not adjust, we would expect more collisions to occur and the pressure to go up. And in Charles law situations, the volume does actually adjust to keep the pressure constant by keeping the rates of collisions constant, either giving everybody more room to fly around in as they're moving faster to keep the rates of collisions up, or if the temperature drops, the volume drops with it. So now if they're moving slower, they're still going to be able to kind of keep the same number of collisions happening in that smaller volume. That doesn't happen with Guy-Lussac's law that we talked about, where you have a constant volume in a rigid container where the volume will not adjust. Because the volume does not adjust, what we do see is actually the increase or decrease in pressure. As we increase the temperature, again, they're going to fly faster. And in this situation, the volume is not going to move. So we will see more collisions and we will see an increase in the rate of pressure coming up. And vice versa, as we lower the temperature in that Guy-Lussac situation, the volume remains fixed, which means slower moving gas, less collisions, pressure starts to come down. So those are the relationships we saw there. P goes up, V goes down, and V goes up, T goes up, and P goes up, and T goes up, and vice versa on all of these guys here. Any questions on those there? We saw with our Avogadro's relationship, again, the number of moles is proportional to the volume of gas that you have. That's that constant temperature and pressure situation. We also saw, we talked about stoichiometry, where you could kind of bypass some of the ideal gas law and do a volume to volume relationship like we do a mole to mole relationship. And again, because they do not attract or repel each other, as we just talked about, we could do our partial pressures by none of the gases be affected by any other gas that may be present. So what we're going to talk about next is actually the speed of how a gas is moving or how fast a gas is moving. So on the first chart up here on the left, we have nitrogen at 3 different temperatures, and we have nitrogen at 100, 300 Kelvin, and 700 Kelvin. And pretty much the peak of each of these tells us our speed. So at 100, it is moving on average about that fast. The bulk of molecules at 300, we can see it's getting faster. And here at like 700, it is getting even faster. And with the same gas molecule, what we see here is what we would expect. As you increase the temperature, we do see the gas molecules start traveling faster, and vice versa. If you look at the graph going in that direction, as you lower the temperature, the gas molecule is slowing down, basically, if you look at it backwards, I suppose. Now, if we look over here, this is actually 3 different gas molecules. We have helium, nitrogen, and chlorine, all at the same temperature. And at 300 degrees, chlorine is moving about that fast. Nitrogen is moving roughly about that fast. And here, helium is roughly, the bulk of molecules are moving about that fast. It's right about there. The one that's moving the fastest here of these 3 is helium. Again, because as we talked about with that partial pressure, we see that it is lightest of all 3 of those. The heavier chlorine is actually the one that is moving the slowest. So in comparison of gas molecules in terms of how fast they will be moving at the same temperature, the heavier the gas is going to be moving slower in terms of its velocity, and the lighter the gas should be flying around a lot faster. And again, that's why we saw the greater sort of contribution of helium in that problem versus neon when we did the partial pressures. You could actually calculate how fast a gas molecule is moving doing this, which is RMS. That is the root mean square velocity. So that is the root mean square velocity is equal to the square root of 3 times R times the temperature divided by the molar mass. Couple things about this is that R is actually the gas constant R, but not the one for the ideal gas. It's the one that involves energy, 8.314 joules per Kelvin per mole. Now, there's an important relationship here that I think we saw way back when, like the first chapter, maybe the second chapter, and that was the idea that a joule is equal to a kilogram meter squared second squared. And that means that we can actually replace this joule with what is there. And that also has an effect on a couple of other values that we see in here, other than this, which is a temperature that needs to be in Kelvin. This is the molar mass. And when you use this formula, molar mass is typically grams per mole, but you actually have to do the molar mass here as kilograms per mole. That way, those kilograms will cancel out with what we got going on top. So we can't use grams per mole here for the molar mass. Otherwise, unit-wise, you'll be off by a factor there of 1,000. So you have to convert it to kilograms per mole. The good news about the R is it's the same number. It doesn't really matter the units, but the number is the same. So really, it's the molar mass that has to be there. So you could actually calculate the molar mass or the root mean square velocity of any of those gases by using this formula. So why don't we look at those two that we did? Let's do what is the root mean square velocity in meters per second of helium, which was 4.003 grams per mole, and neon, which was 2018 grams per mole. And we'll do it at a 3 RT over the molar mass. Once again, here when we use this, because of the R value, which is 8.314 joules per Kelvin per mole, again, that joule being a kilogram meter squared second squared, that is where the meter squared actually comes from, means that it's basically 8.314 kilograms meter squared second squared Kelvin and mole when we kind of put it in there, when we kind of substitute all those units into it. We do need to convert our molar mass here into kilograms per mole, so we need to divide by 1,000 to do that, and that would get us to 0.00403 kilograms per mole. Also, same thing here, basically divide by 1,000, and that would get us 0.02018 kilograms per mole. Once again, we need those guys in kilograms so that they properly cancel out in terms of the units here. Although we did change the units on R, the number still stays the same because it's a one-to-one relationship between the units there. Now that we have all that, we could do our for helium. Our root mean square velocity would be the square root of 3 times 8.314. Again, using our units there, kilograms, meters squared, second squared, Kelvin, and mole, times our temperature, which also needs to be converted to Kelvin. So we're going to add a 273 to that. Going to give us 300 Kelvin as well. And we're going to divide it by, again, the molar mass here for helium that has been converted into kilograms per mole. Now, in terms of units, kilograms on top will cancel the kilograms on the bottom. The moles on the bottom will cancel the moles on the bottom. The Kelvin will cancel the Kelvin here. Now, the only units we have left are meters squared over second squared. And when we take the square root of it, we will be left with meters per second. So again, that is how the units sort of work out. And if we do all that good stuff, 3 times 8.314 times 300 divided by 0.004003. Don't forget to take the square root. gonna get us, we'll call it 1,367 meters per second as our root square mean velocity for our helium. Any questions on that calculation? Going to do pretty much the same calculation for our neon. And that's going to give us the square root of 3 times 8.314 kilograms meter squared, second squared, Kelvin and mole, our 300 Kelvin. And again, here using our kilograms per mole of our molar mass. Kilograms cancel, Kelvin cancel, moles again cancel, leaving us again the same meters squared per second squared. We're going to take 3 times 8.314 times our 300 divided by 0.02018. Now a little square root action. If my calculator works, that is not the square root. Try that again. All right, yeah. That looks a little better, I think. All right. So that's going to get us, we'll call it 609 meters per second in this case. Yeah. So this also helps us understand that partial pressure problem we did earlier. I would say that it looks like helium is moving roughly twice as fast, right, as we have our neon moving, which would account for why, again, they accounted for like 12.4, I think it was, or something like that, in terms of the partial pressure versus the 2 that the neon had, because it's definitely traveling a lot faster. For a reference point, helium is moving roughly about 3,000 miles per hour. Yeah. And neon is moving super slow at 1,300 miles per hour. They're both still moving very, very fast. Yeah. But obviously our lighter, faster moving helium is flying around a much faster. Any questions on that calculation there? Okay. Then let's talk about a couple other things involving gases and how they move. Gas diffusion is the gradual mixing of molecules to another based on their kinetic property. So we have some hydrochloric acid, I think, over here. I think that's it right there. Yeah. So we got a little ammonia over here. I guess blue would not be a good choice of color there. Let's try red maybe. Got some ammonia over here. We got some hydrochloric acid moving over here. And in this case, they're going to mix to make a little ammonium chloride in this case, which is the white sort of powder that we see there, or fumes. Why is all the mixing happening over here? This is roughly 17 grams per mole. This is roughly 36 grams per mole. Which one should be moving faster? This guy, yes. So he's moving faster, which means he's moving slower, which means the mixing is occurring closer to the slower moving gas molecules, which is what we're seeing here. And if we can actually look at a formula here, this is the rate at which it's moving for our first compound there. And that is the molar mass of the first compound. And this is actually in grams per mole, this molar mass. This is the second rate and the second molar mass. And obviously, if you knew 3 of the 4 things there, you could figure out either a rate of how fast something's moving. You could also figure out the molar mass of a gas if you're not sure. So gas diffusion is the mixing molecules based on kind of how fast one's moving versus the other and where they'll meet to sort of mix. Any questions on that? And there's also gas effusion, and gas effusion is the process where one gas sort of travels out from one side of a container to the other through an opening. As you can see here, kind of pops out the opening right about there into the other side. And we also have pretty much the same formula there. We have R1 divided by R2, which is our rate, equals T2 over T1. That's our time, actually. And again, our molar masses in grams per mole of each one. So we could actually use some of this information to help us calculate things like maybe we know the rate of effusion of an unknown gas, versus a known gas. So for example, if we look at this problem here, nickel forms a gas compound with the form of NiCO, and we're not sure. What is the value of X here? If under the same conditions, methane effuses 3.3 times faster than that compound. So we can use this information to help us. We know methane's molar mass is 12.01 plus 4 times 1.008 from the periodic table. That's going to give us a molar mass of methane of about 1604 grams per mole. So we could call this, if we want, M1 is our methane, and we would know that R1 is going to be moving 3.3 times faster than the compound. So that's basically 3.3 times faster than R2, right? Which R2 would be our unknown. And our M2 here would be the molar mass, basically, of our unknown. So we could use that information and the formula that we see there to help us solve this. So if we go into this, we have R1, which is 3.3 times that of R2 divided by R2. That's going to equal the square root of M2, which is our molar mass of our unknown compound, divided by the molar mass of our known compound, which is methane, 16.04 grams per mole. The R2s are going to cancel, which means we have 3.3 equals the square root of M2 divided by 1604. To get rid of the square root, I need to square both sides. So I'm going to square both sides. And when I square both sides, that's going to give me 3.3. I should probably square it. That would be good. Like 10.89 is equal to M2 over 16.04 grams per mole. As obviously just the square root there goes away when we square it. We're going to multiply the 1604 to the other side. And that's going to give us a molar mass for our unknown compound of about 174.7 grams per mole. First off, any questions on that calculation? Does it really matter which one I call 1 and 2? It doesn't, as long as you keep the information that goes together. So as long as you keep like the 3.3 times whatever, it goes with the methane. Yeah. It is. So in this case, we could leave it in grams per mole because the only reason we did the other one in kilograms per mole is because we have that R value in there. And that's the only way that the units are going to cancel out correctly. So there's no R in this one. So you could leave it as the normal units per molar mass in this case. Other questions? So how does this help us? Well, we know a couple of things. We know we have at least one nickel in that formula. So we could take a periodic table, hold it at some distance where you can read it. I don't know what that says, even at that distance. I still don't know what that says. It's like 50 point something, I think. Or what is that? Nickel is, this is like the smallest. Is it 58? Oh, wow, that's an 8. Who knew? So that is 50. What'd you say? 58? 69. Thank you. So 58.69 of that is from nickel. I'm just going to say that's really printed small. This is really not my eyes. And so if we subtract that from our molar mass that we got there, we're going to subtract 58.69. That's going to leave us roughly about 116 grams per mole. That's going to be made up basically of a carbon and oxygen unit, right? And we know carbon is 12.01. And we know oxygen is 16. That means each of those CO units is about 28 grams per mole. So if I take my 116 I got left over and I divide it by 2801, that's going to tell me roughly it's about a 4 and some change. And that means that the X value here should actually be 4. And that would tell us that the formula here for this unknown compound would be something like that in this particular case. So we could use this, obviously, as you can see here, to solve for like an unknown compound. If we could do some comparison and how fast or slow that they effuse, or obviously we could just plug and chug into there and solve for one of the four things that are present. Any questions on effusion? 58, you say? That's good. All right. Then we're going to finish up this chapter talking about deviations from ideal gases. So before we talked about, or we've been talking about pretty much ideal gases the whole time. When we deviate from the ideal situation, these are sometimes referred to as real gases, unlike those fake ones, or non-ideal gases. And when we do start to deviate from ideal situations, we actually have to take into account those two things that we saw for the kinetic molecular theory of gases that we sort of ignore. And the two things are the actual volume of the gas molecule itself, and also the attraction forces and repulsion type forces there are between different gas molecules. So under these sort of really non-ideal situations, we have to take both of those things into account. And you can see here, as we get to super high pressures, which is where this situation sort of occurs, are really low temperatures, we have these sort of non-ideal situation. The ideal situation is this straight line straight across, and that's taking the ideal gas law, and you basically get a ratio of 1. And it starts to really deviate as you sort of get into really high pressures and also really low temperatures. So if we just think logically about if I have a really high pressure, which I would say those are pretty high pressures, my volume should be very large or small? Should be really small, right? Boyle's law, right? High pressure, small volume. So at really high pressures, you have a really small volume. So that is why in these situations, we have to take into account the volume of the gas itself. The vast gas molecule now is in a very small container in a sense, and its volume is now relevant versus what it was not in an ideal situation. It's kind of like if you took a golf ball or something like that, or something really small, a small marble, maybe a better example, and you throw it into that trash can. The volume of the marble versus the volume of that trash can, not really comparable, right? Most of the volume is going to be that trash can. You took like a basketball and try to throw it in there, right? Now the volume of that basketball is going to make pretty big difference in that container because it's too small. So that's why under these really high pressures, we got these very small volumes. The volume of the gas molecule is also really important. The other factor is if they're all crammed into this small volume under these really high pressures, and you throw in there some low temperatures, that means my gas molecules are going to be moving much slower, which means they are now going to be very close to each other and hanging out by each other for a much longer period of time, which means you are going to get interactions that are going to occur, like these repulsive forces and these attractive forces that occur, where we don't really see that in an ideal situation. We could kind of ignore that. Why can we ignore it in an ideal situation? Normal pressures are where? Normal standard pressure is 1, yeah, which is like right here. And even if you deviate a little bit more than 1, you know, they're still pretty much hanging out in an ideal situation. You know, you got to get out pretty far in terms of pressures, which we don't usually deal with in normal situations, right? 100, 200, 300 atmospheres to get some really big deviation from an ideal situation. So that's why in a lot of cases we assume ideal gases, because we could nicely use the ideal gas law. It's kind of like a universal gas law for any type of gas that you want to use it for in these ideal situations. And even if it's slightly greater than 1 atmosphere, it's not going to deviate all that much until you get to really high pressures and low temperatures, where you'll really start to see some serious deviations from ideal. So under the ideal gas laws we talked about, those are the two main things that make them. And when we hit these really low temperatures, as we were just talking about, and high pressures, these assumptions really don't hold up because we really have a lot more interaction between the molecules, and they are flying around in a much smaller volume, which means the volume of themselves is really important. And we start to see some deviation from that 22.414 number under STP conditions as we get into those non-ideal conditions. So because real molecules do take up space, their molar volume is larger than what would be predicted by the ideal gas law. And that's what we see here in the ideal gas law. This line on the bottom is sort of the molar volume. But what we see in a real gas situation is we actually will see it being a little bit larger there as we go through with these higher and higher pressures. So we're starting to get some pretty good deviation, as we cross over into a pretty big pressure build up there at about 200 or more, and we start to see that deviation. And this again is why under a lot of cases we assume ideal, because there's not much difference between the two, right? Until we hit those kind of really big pressures, and now we start to see the deviation between a real gas and an ideal gas. So the effect of the molecular volume, and this was worked out by a guy named van der Waals, who did a lot of work, as we'll talk about in the next chapter, with intermolecular forces, how molecules interact with one another. And he did some correction values that you use in a real gas situation or a non-ideal gas situation. And these are what are sometimes referred to as the van der Waals constants. And there's a van der Waals constant A and a van der Waals constant B. And they are specific for specific gases. So different gases will have different van der Waals sort of constants, which again makes it more of a specific type situation when you're doing these type of calculation. So this is a correction for the volume of the gas itself, having to take it into account, kind of the ideal gas law there with some additives there. We have nRT over P. That's all the ideal gas law stuff. So same units as you would use in the ideal gas law, moles and our R value or temperature in Kelvin or pressure. This is still moles, but this is a value that you would look up in a table, which is van der Waals constant there for a specific gas. So you would have to go to that table, find the gas, and find the constant. If you ever have to do that, you should also be very careful of the table you look at, because the units they use may be very different than the ones that you're using in the ideal gas law. So you want to make sure you always trying to check your units if you have to look up those values. Now, in addition, the other thing that's affected is the pressure. And that's again because of the attractive forces that we see and repulsion forces that we see. And once again here, we start to see some deviation happening between an ideal gas and a non-ideal situation when we start to drop our temperature to low temperatures here, right? Because this is in Kelvin, so that's like 0 Kelvin would be minus 273 Celsius, right? So low temperatures. So as we drop those temperatures down, as we talked about, we're now going to have these gas molecules moving much slower. So again, they're going to be interacting with each other because they're just going to be by each other for a much longer period of time. So we're going to start to get some interaction that's going to happen between the different gas molecules, and that's going to affect the pressure that we see. And van der Waals had a correction value for the pressure associated with those attractive forces, and that's van der Waals A constant, which again is a value that you would look up on the table, and that's our nRT minus A N over V squared. And the attractive forces, as I showed you earlier, as we get this attractive forces, because this gas molecule is really not flying around super fast at this point, they're going to have some attractive forces, which can sort of slow this guy's, as I mentioned before, sort of roll into the wall there. And that will obviously have effect on the number of collisions that we see in a real gas situation, and obviously can affect the pressure. So what do we do with all those correction values? We get a very scary looking equation, which is sometimes referred to as the van der Waals equation, which is used for non-ideal gas or real gases. It is like the ideal gas law, extra, I guess, I suppose. So we have really our PV equals nRT, like our ideal gas law. Here is our corrective value, our factor there to affect the pressure. as a result of the interaction between gas molecules. This is our corrected value that's been inserted in there to correct for the volume of the gas itself. This is a table, as I was mentioning, that you could look up specifically for different gas molecules for the A value and the B value. And again, you have to look it up for different gas molecules. How do you solve it? The same way. Yeah, so you plug everything in and solve for whatever is missing in that particular case. The reason we oftentimes will assume ideal situations is the ideal gas law is a more universal gas law because you don't have to find the specific correction values for the specific gases. And since, as we saw in that first diagram, even at a little higher pressures than 1 atmosphere, it doesn't deviate all that much until you get to really high pressures. So it's usually safe to assume ideal conditions, and why we use the ideal gas law in pretty much all the calculations, and we assume that ideal conditions, so we don't have to go use this one. But if you are at a situation where it's really high pressures and low temperatures and it is sort of a real gas situation or non-ideal